We're now going to take a look at some of the properties of waves. The first important property is the property of reflection. When a wave encounters an interface between two media, for instance, let's say one type of rope and another rope, or between water and, for instance, the beach, some or all of the wave may be reflected. So an example of that that's pretty simple is an example, for instance, of a rope that might be attached to some sort of maybe a ring and then have a ring stand at the end. So this is an example that is often used in books. An equivalent of that is our little wave generator, where you have a bunch of rods along here and you generate the rods, and at the end you let the end of it go up and down. Here I've just got a rope, and the rope is attached to some sort of a ring stand, and this end is allowed to go freely up or down. Now, I send a pulse like this. This is known as the incident pulse. When the pulse gets to the end, it's going to pull this ring up. But the pulse cannot be transmitted into the second medium because there's no rope over here. What will happen in this case is that when it hits here, it will be bounced back, i.e. reflected. And what's important is that it will still be on top of the rope. So on its way back, it'll look exactly the same. I'll draw that maybe like here. But it'll be on top and it'll be headed back that direction. And I've drawn it a little higher just so that you can see it. So wave comes in, wave pulse goes back, pulse was on top, pulse is on top, no phase change. And the reason that no phase change occurred is because this ring was free and easy to move. That is to say, like there's no density of the medium over here because it has no mass. So let me show you this in a video. In this case, we're going to connect the rope with its pulse on top, but we're going to connect it to something much more massive. And that massive thing could be your hand holding the rod of your wave generator over here, or we could just be attaching it to the wall here. Now, as the pulse moves along and hits the new medium, it cannot pull this point up, and consequently, as we'll learn later on, there has to be an interference between two waves. The second wave, the reflected wave, that's going to be sent back is going to be sent back, but it's going to be sent upside down with a hump like this. So it's an inverted reflected wave. Because phase is extremely important with this concept of interference that we'll cover in a little bit, this is a very important thing to note, that the phase is changed 180 degrees, or another way of saying it is inverted, or you can say half a wavelength. This will be really useful when we get back later on in the semester to deal with light and optics. For instance, this is one of the things you can do with coatings to stop reflected glare and such. So, if you hit something more massive, it flips the wave upside down. Again, I'll use my wave generator and show you a video with this occurring. This leads us to what is called the law of reflection. When one sends a wave, one can think about it having wave fronts and a ray, and the ray showing the direction of propagation. If that hits a medium, we can think of there being a normal, just like the normal force that we studied previously, and that normal is perpendicular to the surface of the interface, where this represents the split between medium 1 and medium 2. So this wave was going like this at an angle. This angle right here on the inward side is called the angle of incidence, theta sub I, sometimes called theta 1. And on the other side, after it strikes, it'll bounce off at an angle, and that angle is called theta R. This is the reflected angle. And the angle of reflection says something very simple. It says the angle of incidence is equal to the angle of reflection. So if you come in at 30 degrees with respect to the normal, you bounce off at 30 degrees with respect to the normal. Now you see the same effect when you watch pool balls strike a pool table, and in fact Newton didn't understand or know that light was wave, yet he built a reflecting telescope. And it acts as if the wave coming in is like a baseball or tennis ball or pool ball and bounces off. Now here's why Newton would have said that this occurs. He would have said, look, there is a force applied if you think of this wave coming in like a little baseball, and that force is going to be along the normal. So the only change in momentum will be perpendicular to this surface. Any momentum in this direction must be maintained. So Newton's idea was to think, hey, this had some px, and afterwards it still had to have the same amount of px. So these two sides of the triangle have to be the same. On this way, the momentum is going down. But when it hits, Newton would have said the momentum would have to go up. And it would have to be exactly the same amount of momentum that it had on the way in, except it's changed direction. So this side of the triangle would have to be the same. Well, if these two sides of the triangle are the same, these are similar triangles, and this angle here is going to be the same. And so that's the geometrical way by which Newton did it. There is a more advanced way of looking at this from a wave perspective, but we don't need to cover it here. The bottom line is simply to know that the angle of incidence is equal to the angle of reflection, and when we're talking about these angles, they're measured with respect to this perpendicular called the normal that's perpendicular to the interface. The other thing, just to make sure that we're clear, what we're talking about from a wave perspective is to remember that when we talk about these, although we draw arrows for these rays, this is really a wave. So there's really a wave front coming down. The ray is perpendicular to that wave front. When it strikes whichever part of the wave, it causes matter inside of here to start oscillating, and they create new waves. And those new waves are the waves that produce new fronts like this, and those are the waves whose ray is pointing like this. And if I did that right, so that this angle and this angle are the same, it is really spread out. It's really not these arrows, but it works just like the arrows, and it's easy to think of them as the arrows. So we often treat these more like the ray, what they call geometrical optics, rather than dealing with them as a wave. But they are waves. Okay, that finishes this particular thing. I want to show you a video where we actually see that the angle of incidence is equal to the angle of reflection. And for that, I'm going to use light, which is a wave. Here we see a light ray coming in, striking an interface, and being reflected. The normal is placed down here along 180, so the difference from 180 and this is the reflected ray, which is about 43 degrees. Likewise, here's the instant ray, and from 180 to about 223 is 43 degrees. So this angle is equal to the angle of reflection. If we adjust the light to 50 degrees, we see 50 degrees here, 50 degrees there. We can adjust it to 60 degrees. We can adjust it to 70 degrees and even further out. In each case, the angle here, that's the instant angle, is equal to the angle of reflection.